Hello, everyone, and welcome. My name is Rula Deeb. I'm a senior principal at Geosyntec Consultants in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. I have the pleasure of facilitating today's event. This webinar features DoD-funded research efforts to identify reliable techniques for detailed survey of unexploded ordnance at underwater remediation sites. Dr. Dan Brown from Pennsylvania State University will discuss the development of the Sediment Volume Search Sonar sensor system, which utilizes a novel form of three-dimensional synthetic aperture sonar imagery best suited for remediation sites with less than 5 meters of water depth, so very shallow sites. A description of the device's new acoustic receiver subsystem and progress on its fabrication will be discussed by Dan. His presentation will be followed by a Q&A session. The next several slides provide instructions on optimizing your webinar experience. If you have not done so already, please download Zoom at the link shown here and provide it to you in your webinar registration confirmation email. If you cannot download Zoom, you can view the slides using a compatible internet browser, such as Firefox, IE, or Edge, and by creating a free Zoom account. If you're unable to view the slide or if your screen freezes, try keying Control and F5 to perform a hard refresh of your screen. If you're accessing the audio through your computer, click the arrow next to the Join Audio button, select the speaker and microphone, and follow the prompts as they appear on your screen. If you continue to experience difficulties, please call into the conference line provided to you in your registration confirmation email. You can also submit a comment using the chat box on your screen. Please use the chat box only for comments related to technical difficulties. The Q&A option should be reserved for questions for today's speaker. And in case of continued technical difficulties, you can always download a PDF of the slides from the webinar webpage and call into the conference line. We will be live streaming the webinar on the SERDP and ESTCP YouTube channel, the link shown here. So that's another way you can follow today's proceedings. The broadcast is listen only. You can submit questions by using the Q&A box on your screen. Please don't wait until the Q&A session to submit your questions. We do encourage you to get them in well in advance of that session. When you submit your questions, please add your organization name at the end of your question so that we can identify it during the Q&A session. With that, I would like to introduce Dr. David Bradley, who is the SERDP and ESTCP Program Manager for Munitions Response. Dr. Bradley's professional career includes U.S. Navy-supported research, laboratory directorship at the NATO Undersea Research Center in Italy, and research and academic activities at Pennsylvania State University's Applied Research Lab. As an emeritus professor of acoustics, he published a lot on the topic, and he is currently a University of Washington Applied Physics Laboratory staff member assigned to the SERDP ESTCP Program Office. Dr. Bradley is a fellow of the Acoustical Society and has chaired society committees and served as president. Dave, please proceed.
Thanks, Rula, and welcome everybody. I'm really looking forward to Dan's presentation. He and the Penn State team have been doing a fantastic job, and I'm sure you will find it extremely interesting. The next few slides, it will give you a quick overview of SERDP and ESTCP. As you can see, the SERDP is a science and technology focused program area. It's multi-agency, DoD, DOE, and EPA, as you see. The companion program, ESTCP, is more in the nature of, as it says below that acronym, demonstration and validation, and I would add transition to the user community. It is contrary to SERDP, ESTCP is actually a Department of Defense program only. There's several environmental drivers for the type of work supported, and you can see the details next to each of the pictures on the view graph. The main point I would make is simply that we're concerned with being able to sustain and develop and maintain ranges, facilities, and operational operations. I guess I picked the wrong adjective there. Operations by the military forces. A second sort of set of environmental drivers is the reduction of current and future environmental liabilities. As you see in this, again, there's some details under each respective picture, but our goal is to do exactly what you see under the words environmental drivers. We have several main focus areas. They're listed here. The PFAS and AFFF has been in the news so much that I can't imagine anybody listening to this has not heard about it. This particular webinar, of course, has a focus of munitions remediation, but you see the list of focus areas, and this is an overview list. I might add, there's significantly more when you get into the details. The website that's at the top of this page is a wonderful resource with not just administrative information, but a wealth of technical information as well. And I would urge you, if you don't use it on a regular basis, to please do so. One of our responsibilities to Congress is to publish as much as we possibly can in the open literature. So many of our technical reports with a lot of technical detail are accessible at the website. The webinar series, which this is the one of obviously today, and you can see the continuing list. They're kind of a couple, in round numbers, a couple of months, couple per month, and obviously the topics vary with respect to the various program areas. The webinar series, again, visit the website and go to webinars, and you'll get all the detail you need to join with them. And I'd like to close because it's coming right around the corner with an urge for everyone listening to join us at the symposium. It's being held in Arlington. And again, if you go to the website or the direct site for the symposium at the bottom of this page, there's plenty of detail. And so let me stop with that and get you back to the main person that's going to be talking with you today. Dan, it's over to you.
Thank you so much, Dave. And before we turn it over to Dan completely, let me go ahead and introduce him. Dr. Daniel Brown is an assistant research professor and head of the Sensor Analysis and Data Modeling Department at the Applied Research Lab at Penn State. His current research interests include synthetic aperture sonar signal processing, sonar system performance modeling, acoustic navigation, and coherence of scattering from random rough surfaces. Prior to working at ARL, Dan served as a scientist for the Naval Surface Warfare Center in Panama City, Florida, where his work focused on the development of signal processing algorithms for synthetic aperture sonar systems. Dan received a bachelor's degree in physics from Rhodes College in Tennessee, a master's degree in physics from the University of Mississippi in Oxford and a doctoral degree in acoustics from Penn State. Dan, we're delighted to have you. Please go ahead and get us started.
Rula, thank you for the introduction, and first of all, thank you to your team for all the work you've done to help prepare for this. It's always a pleasure. And then Dave, I appreciate the invitation and the opportunity to speak at the webinar. So today I'm going to be talking about the work that has been going on here at the Applied Research Lab at Penn State towards addressing the question of how do we conduct detailed surveys for unexploded ordnance in very shallow water. Before we get into the talk here, I guess I wanted to call out a couple of people that I wanted to acknowledge. First of all, I'm supported on this effort by two co-principal investigators, Sean Johnson and Cale Brownstead. Sean supports this effort in a number of ways, but with a particular emphasis towards modeling of sonar systems and modeling of the performance of those sonar systems. And Cale supports the program through acting as a sonar system engineer. So without those two guys, I'd be lost, and they've been a great help. Additionally, as you'll see in this brief, there's quite a bit of work that's been going on at Penn State in developing new sonar hardware specifically for the purpose of very shallow water surveys. And that sonar hardware design is supported by a large team of design engineers and fabricating technicians. And without that team, we couldn't be successful. So I wanted to acknowledge them. And then finally, we work with a number of external collaborators. Early in these efforts, we worked with Aubrey Espana and Steve Cargill at the Applied Physics Laboratory at the University of Washington, and Joe Calantoni and Ed Braithwaite at NRL Stennis. And so to those collaborators, I wanted to say thank you. And finally, at the end of this talk, I'll point to our machine learning collaborators, which are growing by the day, and we're participating with a large and diverse set of different people that are pursuing different machine learning objectives with this data set. Okay, so with that, we'll jump into the talk here. So to give a little bit of an outline of where we'll be going here, at first we're going to define the kind of background problem around the idea of conducting ordnance surveys, detailed ordnance surveys in marine environments. We'll identify some of the challenges there, and then some of the even more specific challenges associated with operating in very shallow water. Those challenges led us towards the development of a platform with an integrated sensor that is purpose-built and meant to address the specific challenges associated with very shallow water surveys. That sensor that's been developed and integrated to that platform has been deployed to a couple of different testing sites that we've developed. And so we'll look at some of those testing sites and what our objectives were in those sites. And then we've collected quite a bit of data at those sites that we will then show some examples from. And the sensor that we're developing here, it generates acoustic imagery, similar to the type of imagery in some ways that you might see in a medical ultrasound type scenario, where we're generating three-dimensional imagery within the seabed or within the lake bed. And so that three-dimensional imagery requires some special ways to handle it for visualization, because as humans, we're used to looking at 2D representations of things. So we'll look at some techniques for visualizing that 3D imagery. And in looking through that imagery, one of the things that we're going to find is this persistent phenomena associated with many man-made objects, where we're seeing what we are calling late time scattering. That is energy that is coming out from the target at a time that doesn't correspond to the range to the target. We'll talk about the origins of that, where that comes from, and how it might provide us with a discriminatory signal that will help us separate potentially man-made objects from natural clutter objects. That notion of late time energy, this late time scattering phenomena that we see, has been the focus of quite a bit of the signal processing development that we've been engaging in over the past year to year and a half. And we'll look at two different threads where we're driving our signal processing algorithm development to better exploit the late time scattering phenomena to enhance its detectability and to try and separate it from background scattering so that potentially we can mine it for more discriminatory information. And really that finally drives us to the last piece. We're going to look at 3 different machine learning collaborations that we have ongoing with 3 different groups of people that are all leveraging the data that we've been collecting with the SVSS system. And so we'll look at how they're applying machine learning to this novel 3-dimensional data set, and then we'll start to draw some strings back up to the signal processing development to see how that processing that we've been developing might inform the later development of these machine learning collaborations. And then, of course, we're going to wrap up with an assessment of how this work and how this program can provide benefits to the Department of Defense. Okay. So jumping in to just give us some background, on marine surveys for unexploded ordnance, we have this problem that we're trying to address related to the fact that historical military activities have resulted in quite a number of items of unexploded ordnance that are distributed across marine environments. And here in this photo that I show on the right, what we can see is a number of unexploded ordnance that have been recovered by a team. They're placed here on the beach. We can see these are heavily fouled, so they have a lot of biological growth, but they are obviously ordnance. And the challenge that we have is that when these are in shallow water environments, like this coastal region that we see here, when they're in shallow water environments, we need to have a way to go out and detect and identify those objects. In the terrestrial case, the standard approaches are using electromagnetic systems, right? So we're using electromagnetic sensors on land. These sensors can be brought over a site, and they've been proven to be very, very effective at identifying these types of objects for terrestrial applications. They present, though, this presents a pretty unique and difficult problem in the marine application because of the relative attenuation of electromagnetic energy underwater. And so in marine applications, the sensors that we generally turn to because they have relatively weak attenuation are acoustic sensors. So these are sensors that can have a fairly good standoff from the seabed. They can send out acoustic pulses that can propagate into the bottom and scatter off targets, and then we can use signal processing to recover imagery. The challenge, though, is what are these sensors sensitive to? For the electromagnetic sensors, they are sensitive to metallic objects, right? So it's a very good discriminatory signal which says, oh, if I'm seeing something with a certain dipole moment, I'm seeing something that is metallic, there's a very good chance that it's man-made and it's an object of interest. With acoustic sensors, though, we don't have that discriminatory ability to tell a metallic object from a non-metallic object. An acoustic scattered field is going to be sensitive to changes in the impedance or in the compressional wave sound speed in the seabed. So what we'll see are things that have a density different than the surrounding sediment, or a compressional wave speed or sound speed different than the surrounding sediment. Those are the things that are going to be picked up by our sonar system. This can include natural clutter like rocks, and it can also include the unexploded ordnance. So one of the challenges we face in using acoustics for these problems in these marine environments is separating clutter from man-made objects. So a further challenge that we have here in conducting ordnance surveys in very shallow water is the challenges associated with placing sensors into the very shallow water. We attended a workshop that was hosted by SERDP and ESTCP back in 2013. And in that 2013 workshop, they presented a list of, or a range of, different technologies that had been applied to this problem were presented. And as we looked at those problems, or those sensors that had been applied to this problem space, one thing that was apparent was there was a real capability gap to conduct detailed surveys in very shallow water because it's very difficult to place sensors into very shallow water. Many of the sonar systems that are employed for this type of survey are either hosted aboard an unmanned underwater vehicle. So an unmanned underwater vehicle is a robot that looks something like a long torpedo that might have a sonar system integrated to it, and that robot flies around a site conducting acoustic surveys. Or the other type of platform that these sensors can be deployed from is a towed platform. So this would be some type of sled that's connected to a tow cable that's behind a boat, and the boat pulls the sled through the field, and the sled dives to some depth so that it can conduct the survey. In extremely shallow water, so water depths as shallow as 1 meter or 2 meters, it actually becomes a real engineering challenge to safely deploy those types of platforms to carry sensors, right? The robot sensors or the tow sleds just don't have enough room to operate when you're talking about in a meter of water or 2 meters of water or 3 meters of water. And so what we realized is we needed to come up with a way to identify a platform that could safely operate in those types of environments and carry an acoustic sensor. The other reason that these sites are actually quite important, these water depths are quite important, is that these are the water depths where we're most likely to have human UXO interaction, right? So here, in this diagram shown below, this is in the Chesapeake Bay, and we're showing a UXO, a potential UXO boundary here shown in red. So this is a region that might need to be surveyed for UXO. The water is actually shallow enough in this region that we can see the sandbars that have formed through here. And these are the places where people might actually go into the water, be able to interact with the seabed, and they have the highest probability of being able to physically touch an unexploded ordnance if one was located there. So it's critically important that we develop sensors that can operate in these types of areas. And the challenge that we face is the fact that there weren't any acoustics at the beginning of this effort. There weren't any sensors and platforms that were suited for those water depths. So to address this, we proposed a sensor and platform that we call the Sediment Volume Search Sonar. So the actual sonar system itself is seen here in the forward portion of this pontoon boat. So the sonar system is mounted to this black metal plate. You can see the cables and connectors carrying all the wires that attach to the hydrophones and the projectors on there. And so we transit out to some site where we want to conduct a survey, and we use this little crane arm here, and it lowers this plate into the water down beneath the pontoons, right? So we transit to the site with the array plate up, and then when we get to the site and we're ready to conduct the survey, we lower the sonar system into the water, and now we're configured into a mode where we're ready to conduct our acoustic survey. The sonar system insonifies downward, so the sonar system is looking straight down into the bottom, and it's insonifying a relatively wide swath. So it's insonifying a beam that's about 50 degrees wide when we're operating with our maximum beam width. And the end result is, as we survey some site, we are operating the sonar system in a way where we send out a pulse of sound from one of our projectors. So you can think of the projector as like the underwater loudspeaker. It sends the sound into the water. The sound propagates down through the water. It actually propagates to the lake bed or seabed, and it can propagate then into that seabed. All along the way, it's scattering off of the seabed itself and any objects that are buried within the seabed. We apply a form of signal processing known as synthetic aperture sonar signal processing. And what we generate then is a three-dimensional volumetric view of the items that are within the seabed and the seabed itself. This is an example slice. So this is an example two-dimensional slice taken from within the seabed. And in this case, we are looking 11 centimeters into the seabed, and we can see this long cylindrical object called out here. This actual data set was collected at a local lake where we have installed a number of targets. The local lake that we use here is actually an Army Corps of Engineers flood control reservoir. And every year in March, the lake is drained by about 20 feet. And so when the lake is drained by 20 feet, we get access to the lake bed. It allows us to go out and dig holes and place objects of scientific interest and also certified inert munitions, so that in the spring, summer, and fall, we can come back out and conduct acoustic surveys. So the object that you're actually seeing right here, called out in this red box, is this solid aluminum cylinder that we buried in the lake and have good ground truth on its location. This is another cylinder, half the length of the one shown above, that we buried in the lake in that position as well. So the Sediment Volume Search Sonar program, the purpose of this program is to develop a sensor and a platform that is dedicated and designed for detailed unexploded ordnance surveys with a particular emphasis on very shallow water operations, water depths as shallow as 1 meter. It's a very technology development focused project. So we're focused on identifying the surface craft and the sonar system that's capable of operating in very shallow water. How do we design that sonar system? And how do we design the signal processing that goes along with that sonar system so that we can support imaging of the sub-bottom and the interface to identify unexploded ordnance and buried unexploded ordnance. The effort has had, this program has had a significant effort in developing purpose-built sonar hardware that's been tailored to this ordnance imaging, this detailed ordnance survey problem. So here's 2 different phases of the sonar hardware development that we've engaged in under this effort. On the left-hand side, what we're showing here is the prototype SVSS hardware. So this prototype SVSS hardware was the initial hardware that we deployed under our initial effort for SERDP. In that effort, what we wanted to try and do was get out to the field as quickly as we could to get lessons learned under our belt so that we could inform a purpose-built design. Along those lines, we then tried to leverage existing hardware that's here at ARL Penn State to the greatest extent possible. So we started out with these 8-channel hydrophone arrays shown here in a configuration, a 2x4 configuration. These hydrophone arrays had been built for another program, and so we already had access to these. And in some sense, we treat them almost like Legos, right? These are devices that exist for us. We can reconfigure them on an array plate on this pontoon boat. And so we have 10 of these hydrophone modules, 10 of these 8-channel modules, and we arranged them in this T shape, giving us an 80-channel receive array. In addition to that, we needed a set of projectors so that we could pulse sound into the water. So the projectors act like those underwater loudspeakers. And we did not have access to a projector that operated in the correct range of frequencies. But one thing that we did have access to were the components of a projector that operated in the correct range of frequencies. So we had access to these individual elements that sit inside of our projector. So these heads vibrate back and forth to push sound out into the water. And so we were able to leverage these existing internal elements shown here and then efficiently repackage them into a 4x4 grid, making up these brown squares here that are our sonar projectors. Those are the items that are pulsing sound into the water. Using this approach, we were able to very quickly integrate a sensor capable of testing from the test platform that we already had, deploy it, and conduct a number of tests both at our local lake, the Sayers Reservoir, where we installed the target field, and also a test that we conducted at the Aberdeen Proving Grounds in the littoral warfare environment. But based upon the lessons learned from analyzing that data and using this leveraged hardware, we were able to identify what it is that we would have wanted to have from a blank sheet design. So what purpose-built hardware would we want to bring in order to maximize the performance for this very shallow water sub-bottom imaging problem? And so we've since designed a purpose-built projector shown here. So we've designed a new set of elements that are shown here with their green heads in this 4x4 configuration, similar to this, but a little bit smaller. This new projector has an added advantage in that it allows us to have access to pairs of electrical channels so that we can vary the transmit beam width as a function of frequency if we desire, so we get a bit more flexibility. Additionally, moving from our old projector, we were able to operate over a range of frequencies from 20 to 35 kilohertz. And here in our new projector, we're able to operate from 12 to 44 kilohertz, all while providing a substantial boost in the transmit source level. So we can put a lot more sound in the water over a much wider range of frequencies. This gives us higher signal to noise ratio on the data that we're recording and gives us more information, more bandwidth to work with to interrogate the targets over a wider range of frequencies. We're currently coming through the final stages of fabrication of our new hydrophone array. So we're moving away from our 2x4 configuration into a 1x8 configuration with an integrated preamplifier here. So these new hydrophone array elements actually are going to give us the ability to greatly expand the dynamic range of this sonar system. In fact, we're able to extend beyond a 16-bit dynamic range. So we're going to be digitizing this data with 24-bit receiver cards, and we anticipate that we will have in excess of 18 bits of dynamic range available from this. So we're going to be able to receive signals that are much weaker than we had been able to with the old array design. In relaying out the plate that all of our sonar hardware mounts to, we actually afforded ourselves a really nifty opportunity. We're actually going to deploy some of the older style hydrophones ahead of the newer style hydrophones so we can do an A/B comparison and understand their relative performance. I mentioned two different test sites. So we've developed test sites both at the Foster Joseph Sayers Reservoir, that's our local lake that we test at, and at the Aberdeen Proving Grounds Littoral Warfare Environment. These are photos from our test site installation at the Littoral Warfare Environment. When we establish a test site, we deploy a mixture of ordnance, a mixture of science objects, so solid cylinders and pipes, and then a mixture of clutter where we have stones and rocks that we'll deploy to the site as well. We deploy these sites on a very tight grid. So here you can see in this case at this site we had 86 total positions called out, and we had those positions on a 2 meter by 2 meter grid. So at this site we deployed 86 objects. At our local site we have 78 objects deployed. So between our two sites we have over 150 objects. Over 150 objects deployed, and in conducting our demonstrations and trials at these sites, we've collected multiple looks from multiple different directions across all of these objects, really forming a very large data set, a very large labeled data set that we're able to provide to the SERDP machine learning research community to enable their development of new and novel algorithms for automatically finding these objects. Additionally, for us, it allows us to understand how our signal processing algorithms behave as we pass over objects at different angles, at different offsets beneath the sonar system. So the imagery that we generate, I've already mentioned that it's three-dimensional imagery. So unlike a photo that you might take with your digital camera, instead, a photo you might take with a digital camera is a 2D representation of pixels. Here, what we have is we have a three-dimensional representation. So you can almost think of it as multiple layers of pictures, if you want to think of that, going in depth. And instead of describing them as consisting of pixels, since they're volumetric in nature, we refer to the individual elements as voxels. And so when we create this three-dimensional data, the way the sonar system works is in the along track direction. So the along track direction is the direction that the boat is traveling, that the sonar is traveling. We use a technique called synthetic aperture sonar beamforming or synthetic aperture sonar reconstruction. And so in that direction, what we are doing is we are transmitting a sequence of pulses at a fixed spatial interval. And then through some fairly advanced signal processing, we are combining all of those pulses together, that multitude of pulses together in a very careful and particular way that allows us to make it appear as if we had a much, much larger sonar system than the physical sonar system that's deployed from the pontoon boat, from our test platform. And so by synthesizing this very large aperture, what we're able to achieve is a high resolution in that along track direction. And in addition to being able to achieve that high resolution in the direction of travel, we can achieve that high resolution as a function of range as well. So the deeper we go in the sediment, we're not losing resolution. We're able to extend that synthetic aperture and maintain that high resolution in the direction of travel. In the cross-track direction, so this would be left to right if you were sitting on board the test platform, or port to starboard, we use a technique known as real aperture reconstruction. So we can't form that long synthetic aperture. So in that direction, we have real aperture resolution, and that's a resolution where the further away we get from the sonar system, the poorer that we're able to resolve the bottom, the poorer our resolution gets, and the more reverberation that we're going to bring in to compete with the returns from our target. Now one technique that we use, and that is used by other groups that do this, is we do use multiple transmitters distributed across the sonar system, so from port to starboard. And so by doing that, we can achieve a benefit or a boost in our real aperture resolution, but still not to the same level of our synthetic aperture resolution. So we generate this three-dimensional imagery, and now we need a way to visualize that imagery. And we're going to see three different techniques. The first technique is going to be known as a projection, where we're going to project that imagery down to 2 dimensions. The second technique is going to be known as slicing, so where we literally are going to reach inside of this and extract 2-dimensional slices from the data. And then finally, we'll look at an example where we use a 3D viewer to try and visualize this imagery. Okay, so here we have our large cube of raw data shown up here in the top right corner. And what we're wanting to do is we're wanting to make 2-dimensional projections of that data so that we can visualize what's present inside of this volume of data. And so if you imagine along this direction, this column going in depth, if you imagine projecting downward and searching this column and saying, what is the brightest voxel? What is the highest amplitude voxel? What is the maximum voxel? I'm going to choose the maximum out of this column and write it to this corner. And now I'm going to go to this column and search for the maximum, and I'll write it here. And I repeat that for all of the different columns in depth. So I'm projecting the maximum along the depth dimension. This is known as the depth maximum intensity projection. And so in some ways, it's like we're looking down from above and looking down through the sonar data and saying, show us all of the brightest returns from inside of the seafloor. And so what we can see pretty clearly is there's some bright object here. We can see some kind of long or some kind of short and skinny object here, a longer, skinnier object here. And then we can see a number of places where we have some kind of small, compact objects. We can also form that maximum intensity projection in other directions. So here we could look in the cross-track direction and project across the track. So in that case, it's almost like we've taken this cube of data and we're looking through it in a sideways direction. And so this would be our cross-track MIP. And now this long, skinny object that was here, we can see that long, skinny object here. This short object that's here, we can see that short object here. And then we can also see a couple of other interesting things. There's something here that has this kind of ghosting effect beneath it, and there's something here that has a ghosting effect beneath it. These 4 positions, here, 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 and here, all correspond to along track positions where we've placed man-made objects buried in the lake bed. That ghosting effect that you see beneath them, these are those late time returns that I alluded to in the overview slide. And so if we look at this image, we can see here, this object is a deeply buried shot put. We can see here, this object is another deeply buried shot put. And then the object here and here are these short and long aluminum cylinders. Each of those objects is creating this late time return that we're able to see fairly clearly. But there's a challenge that we have. There's a challenge that we have in the way that we are looking at this data, right? So because we're using this maximum intensity projection, we're having to look through all of the sediment to find the target of interest. And so if there's anything in the sediment that is at a level louder than the target, it can obscure our ability to see the target. And in one way I think about it is it's almost like going out to look at the stars on a hazy night, right? So there's this background of haze that you're having to look through in order to see the stars that are out in space. Here, we have this kind of haze that is all of the sediment that is closer to us than that is closer to the direction that we're looking and further away, so ahead of and behind the target. We're having to look through that haze to see our target. Another way we can deal with that is to avoid looking through the data. We can start to extract individual slices. So here we could extract just this slice in depth, or at some along track position, we could extract a slice, or at some cross track position, we could extract a slice. And immediately you can see that for this same pair of objects taken from this depth slice or this cross track slice, it's much clearer. The target stands out above that background much more easily. And so this gives us a higher signal to noise ratio look, a look where it's easier for us to find the object. And in fact, you can see called out in pink here, this long cylinder that's buried is clearly visible here, here, and here because we chose slices that pass through each of these. The interesting piece though, and the downside of this is the fact that the slice that's passing through this object does not pass through this object. And so we can see that that small cylinder is not visible in this cross-track slice at 13 centimeters offset from the center line, and that's because we're not passing through it. So the downside of this method is that we're essentially ignoring regions of our data. And so really what this prompts us to is wanting to have ways that we could automate this detection going between these maximum intensity projections, these slices, and then potentially considering the entire data cube as a whole. As I look down on this target though, one thing that's kind of interesting to me is it's very easy to measure the length of this object and the width of its object. Its position is very well defined. It has very crisp edges. And so one of the things that this lets us do is to understand how well we're able to localize these types of targets that we've planted in this field. In order to try and make a quantitative assessment of our ability to localize these targets, we actually chose one cinder block that we had planted in our field at our local lake. This cinder block shown here is oriented so that its flat side is pointed upwards. And here we're showing a slice through the top of that cinder block on a logarithmic scale. And so if we set a threshold where we're going to declare certain voxels in this image as belonging to the top of the cinder block and others as belonging not to the cinder block, we can see that we create a logical mask shown below. So that logical mask in green, these are going to be the pixels or the voxels that we have declared as belonging to the center of the cinder block. And we can calculate the centroid. Where is the middle of the top of this cinder block in this image? Our image reconstruction pipeline that we're using is leveraging the fact that our test platform has an RTK GPS system on it and a high-grade inertial navigation sensor. So our test platform, given the navigation quality that we have, allows us to localize the position of our test platform to less than a centimeter or to order of a centimeter as it transits over the lake. Our image reconstruction pipeline brings that geolocation through to its output data product. And so what that means is for every single pixel in this image, we can actually assign an absolute latitude and longitude to the target. From that, we can compare it to the latitude and longitude ground truth that we measured when we installed the targets. And in this case, for this cinder block, the ground truth for the position of this target that we measured using an RTK GPS system when we deployed the target is shown in red. We can see here that we have between 5 and 10 centimeters offset from the ground truth position and the centroid of our target. Doing repeat passes over this target, so in this case 13 passes over the target, we can see that our RMS contact localization error is 7.2 centimeters, our median is 6 centimeters. So to within an offset of less than 3 inches, we can localize the targets that are deployed in the lakes and test sites where we are testing this sonar system. We have the ability to provide absolute localization in latitude and longitude to something smaller than the width of the head of a shovel. All right, so turning back to these artifacts that we're seeing, in this late time effect behind the target. Here we can see we have a flush buried shot put, short aluminum cylinder, long aluminum cylinder, a buried short cylinder, a buried long cylinder, and a buried shot put. And under most of these objects, we can see this late time effect coming through quite strongly. Here we show it again for a number of other objects where we consistently see beneath man-made objects this late time ringing effect that is appearing. So what is the cause of this? What is the mechanism that is causing us to get this ghosting effect? What we believe this is the fact that we have waves that are coupling to the object or exciting resonant modes in the object. And those waves that couple on and excite these resonant modes within our object are essentially causing the objects to ring like a bell once they've been insonified. Here, this figure is one that we've drawn, but is based on a figure by Williams and Marston in their 1985 JASA paper, where they were discussing how Rayleigh surface waves can couple on to an object. So here we have some plane wave insonifying a cylindrical object shown here, and at some specific angle that is the coupling angle, this plane wave can couple to a Rayleigh wave that then propagates around the surface, the outer surface of this object. As this wave is propagating around the object, it's re-radiating back into the water. So we've coupled something onto this object, a wave that is then propagating around the surface of this object, re-radiating sound. So as this wave propagates around, it will come back around to a position where it re-radiates sound later in time at some offset in time that is then received by our sonar system. So we have this wave propagating around, getting weaker and weaker as it's making these orbits around the target, but re-radiating bursts of sound back to us that we then receive at the sonar system. In the image reconstruction approach that we use for this type of sonar system, we don't account for this mode of acoustic scattering. Instead, the baseline image reconstruction paradigm is one where sound propagates from the source, scatters from the object geometrically. So essentially you want to think about it as the sound bounces off the object, in some ways reflects off the object, and then comes right back to the sonar system. There is no consideration in the standard reconstruction, the standard image formation paradigm, for sound to couple onto the object, propagate on the object, and then return to the sonar system. The end result is that energy that is coming out in this late time is then defocused when it's received by this sonar system. And so if we look at this three-dimensional view of that region where we had the long aluminum cylinder, the short cylinder, and a shot put, what we can see is we have this long cylinder here, we have a short cylinder that's coming by here, and we have a shot put that's buried in here. And for those three objects, we are coupling elastic waves onto the object that may be of the class I described on the prior slide, or other types of resonant scattering phenomena. And they are producing these returns that come out at a later time, and those returns are defocused into the volume. But the thing that I note in looking at this is I see a very large scatterer here. I'm trying to follow it with my mouse carefully. And I see several others that are distributed inside of this sediment that aren't exhibiting these late time returns. And so what we wanted to understand is, well, what are those objects? Is this some image reconstruction artifact, or is this some other object that's in the lake bed? For this depth slice that I've already shown, and it's for that long cylinder and short cylinder, we actually picked out this object that's seen here and this object that is seen here. And we went back out to the lake bed the following year after collecting data and waited until they drained the lake bed, using the fact that we have precise geometric or precise geolocation in our imagery. We were able to identify where we would need to insert a flag to flag this position and this position. And when we inserted the flags in those positions, they struck this rock and this rock that's held in my hand here. So we had large scatterers at a depth that was the same depth as the targets that we were scattering from. And so these large scatterers, these large natural objects weren't exhibiting this elastic behavior, weren't exhibiting this late time return. And so we believe that those late time returns give us a tool to distinguish these man-made objects from these clutter objects that are inside this scene. Okay, so our current work now is on improving our signal processing methods to improve our ability to conduct ordnance detection and classification. So how can we make a better data product so that it is easier to identify regions that have man-made objects and then potentially separate those man-made objects into ordnance and non-ordnance? We're going to look at two different signal processing approaches here. One, late time focusing. So can we adapt our image reconstruction, our image formation algorithms, so that instead of having the late returning energy be defocused into the scene, can we collapse it and improve its contrast, boost its level against the background? And then another technique called signal separation, where what we want to try to do is see if we can come up with a way to cleanly separate those portions of the signal that exhibit a late time return from those portions of the signal that correspond to the more standard scattering physics, the more geometric scattering physics. So can we divorce the two in a way that allows us to still conduct image reconstruction? So for range specific focusing of this late return to try and enhance it, we're leveraging a lot of past work that has existed in this space. So there were papers in 2009, 2011, and 2020 that have all looked at this. In 2009, the application was to try and improve shadow contrast for side-looking SAS imagery. In 2011, the application was looking at multiple scattering and elastic scattering in laboratory tank experiments. In 2020, the work focused on enhancement of the focus for multiply scattered waves in a circular SAS geometry. And so our work has been in adapting this method for a time domain reconstruction pipeline where we attempt to use an all range focusing approach, transitioning over to a range specific focusing approach once we've reached a hypothesized target location. And so an example of what this looks like is shown in these two figures here. And if you're interested more on this, the work that's shown here is actually the work of a PhD student here at Penn State, Kyle Dalton. Kyle's work has been in collaboration with Tom Blanford, who's now at the University of New Hampshire, and myself. And you can find more details on this in his 2022 POMA. Here on the right, what is shown is a simulated data set where a cylinder is shown from a cylinder shown in a vertical orientation. So you can think of the cylinder as being a kind of a circle standing up out of the screen here. And it's insonified by a sonar system transiting along this lower edge, looking upward. And it's a simulation of the return that one might get from a cylindrical a metal cylinder. And what we can see is the initial geometric return from the target, and then we can see this defocused late time return coming from behind the target. By adapting the image reconstruction pipeline to what we're using here on the left, Kyle is using a range varying reconstruction up to this point, and then locking in the focusing parameters to say, I know that all of the scattering that comes from ranges greater than this are actually from a target at this range. So by locking into a range specific focusing algorithm for the remainder of this image, what we can see is the energy that was distributed over a wide range of pixels here has now been collapsed into a narrowly focused tail behind the target, and the overall level in that tail has been boosted. So given this kind of promising initial result, the hope was we could carry this over to field data, and that's exactly what we've done. So this is showing an example of a 155 howitzer shell that was deployed at the littoral warfare environment at the Aberdeen Test Center. This particular howitzer was then flush buried so that it was just barely covered by the sediment. And in this case, this sandy sediment proved to be an extremely strong scatterer, such that when we look through our along track maximum intensity projection and our cross track maximum intensity projection, what we're seeing is we see very little scattering. We cannot distinguish the howitzer from this sediment interface in this view or this view, but we do see the characteristic defocusing beneath this munition, indicating that we've coupled some resonant phenomena onto the object, and it's ringing out in this late time phenomena. By making the hypothesis that there's a target at this depth here and applying this late time focusing approach, what we can see is we can greatly tighten this response beneath the target here and here, improving its contrast relative to the background. So I'm going to go back and forth a couple of times. So defocused, and now applying our range specific focus. So all range focusing and range specific focusing. The real goal here, and the thing that we're quite excited about, is in extending this work and applying machine learning to this to see if this improved contrast of this return allows us to improve our ability to classify this object. One thing that is apparently clear is that if we're attempting to characterize the spectral content of this later return, we can now take a much tighter spatial window around that. We can reject more seabed reverberation, and we should be able to realize a higher signal to reverberation ratio in that region and get a cleaner look at those spectral clues. The other approach that we're taking to try and exploit this late time return is the idea of signal separation using morphological component analysis. In morphological component analysis, what we're essentially doing is we're defining a basis upon which we are going to project our signals to try and split them into separate categories of signals. So the basis that we're using, one portion of it we refer to as the short duration components of the signals. So these are signals whose returns are going to be links that are on the order of the duration of our transmit waveform. So things that look like specular return coming off of the object, and then also long duration returns, which are going to be trying to capture returns that have a characteristic that has them exponentially decaying. And so they will start loud and then get weaker with some time constant that's measured in milliseconds. And the goal of that portion of our basis is to try and capture these late time signatures. And then we're also including a denoising stage that can capture any unwanted noise. And so what we do is we apply these techniques to the raw data collected by the SVSS, and then we can then pass this through our standard image reconstruction pipeline. So if we collected the raw data, applied none of this signal separation, we would generate this original cross-track MIP shown here, where we can clearly see multiple objects and the late returns associated with those objects down below. The short duration signals can also be passed through the same image reconstruction pipeline, and we can see that it's calling out the sub-bottom layering shown here and very strong returns from the targets themselves. And then our long duration image, also passed through our image reconstruction pipeline, does show some scattering from the target, but we can see we've also captured very well this kind of late returning signal into this channel. In essence, we've reduced the amount of seabed reverberation that's present in here by being able to map some of it into this short duration channel. Finally, the denoising output is very interesting. We can see we had some noise that was likely appearing here due to bubbles in our water column. And that's not captured in either the short duration or long duration returns that was captured in our noise channel. The really nifty piece of this is that if we take the single look complex images for the short duration image, the long duration image, and the noise image, and we recombine them together, we get back to this original full image. So there's no loss of information in this process. If you're interested in understanding more about this technique, I would point you to Jeff Gailey's paper. Jeff Gailey has been leading a lot of the development here on these techniques, supported by Ben Cowan as well, and we all have a recent JASA article out that shows some of this. So we've been collaborating heavily with the machine learning research community. The SVSS data sets have been provided to machine learning researchers at Arizona State, at Penn State, and at the NATO Center for Maritime Research and Experimentation. The data sets include extensive sensor documentation, code, and data, more than 3,000 three-dimensional SVSS images, over 100 targets. I believe we're at something like 150 or 160 targets. We have repeat passes over those targets that give multiple looks on every target, and we have high precision navigation that automates target labeling. Our ground truth is sufficiently accurate that when we label the position of where an object should be in the image with our ground truth, the pixel that we are picking out, or the voxel we are picking out, is generally on the object itself. So there's almost no data curation or association that's needed with these data sets. For other machine learning researchers that are supported by SERDP, if you're interested in gaining access to this data, please feel free to reach out to me, and I'm more than happy to facilitate that. So I'm going to give just in closing here, I'm going to give a quick review of some of these collaborations that we're engaging in and we're supporting, and just to give a flavor of the different objectives that are being achieved using the data from this sensor. So MR 211330 is led by Dr. Vishal Manga here at Penn State. And the title of his program is Prior Guided Informed Deep Learning for Detection and Classification of Underwater Military Munitions. The real goal is to try and understand how we can use domain-enriched machine learning approaches with a particular eye towards exploiting that resonance scattering phenomena that we've been seeing, and can we accurately distinguish UXO from clutter and between different UXO types. So here, these are figures shown from a recent paper that was published in Transactions on Geoscience and Remote Sensing. And the approach taken by Dr. Manga and his team is one where there's first a separation between resonant and non-resonant objects. And then once we've separated between resonant and non-resonant objects, the follow-on approach is to separate within different classes of resonant objects. And the three classes that were called out were these spherical shot put objects, the munitions, and then the science objects that we deployed to the field. And what was realized was that as we looked in the maximum intensity projections, both along track and cross track MIPS, was that there were characteristics that were unique to these different target types based upon the structure of how these particular MIPS looked, but also the two-dimensional sequences of slices going down in depth. So this team is looking at applying machine learning techniques, a novel design for a machine learning technique, exploiting these multiple slices, going down in depth, so exploiting all of the three-dimensional information by taking all of the two-dimensional slices, but then also getting these kind of unified views from the along track maximum intensity projection and the cross track maximum intensity projection. If you want to see more about their performance and how this worked, I point you to their recent paper. Another topic that we're collaborating very closely is with Dr. Jayashuria's group at Arizona State. That's supported under MR 211334, Joint Beamforming and Automatic Target Recognition for 3D SAS. Here, there are two different objectives that are being pursued. One is on looking at novel physics-based machine learning algorithms to improve both visualization and ATR performance. And another is in looking at advanced neural networks to being applied to generating SVSS data products. So reaching back from the machine learning application and saying, can we use neural networks to produce higher quality output data products from the Sediment Volume Search Sonar? In that first effort, they looked at developing a new three-dimensional SAS ATR pipeline where they learned a layer that sat before the standard convolutional neural networks that would be used for classification. And the purpose of that layer was to act as a tone mapping operator. So how can we employ a layer that is doing something similar to the dynamic range compression that we do to present information to a human so that they can assess whether a target is present or not? Could we allow a neural network to try to learn that type of tone mapping operator layer, and would that in essence learned pre-processing layer improve the overall performance of an ATR system? The other topic that they have looked at is in understanding how we can use beamforming of the three-dimensional SAS imagery, not through the standard back projection techniques that we use here at Penn State, but instead, can we learn methods that they have termed to be neural volumetric reconstruction? That is, can we allow a machine learning system to work from the raw sensed data, the raw time series, to create higher resolution, improved three-dimensional imagery and data products? Here, they show an example of a standard back projection reconstruction where we can see this cylindrical object called out in this position, and then their proposed method, which shows much tighter boundaries around the object. And so this neural rendering pipeline gives us a path towards potentially enhanced three-dimensional SAS visualization. Finally, the last project that I'll call out is by a colleague that works here with me at ARL Penn State, Dave Williams. His program, MR213543, Advanced Sonar-Based Deep Learning for Underwater UXO Remediation. This effort is really focused on developing ATR algorithms for proud and buried unexploded ordnance using acoustic data from downward-looking sonar systems. Dave's work is focusing on both data from the SVSS and from the MUST system that's in development at APL UW, and the goal is to try and develop ATR systems to provide high detection, high probability of detection and classification with low false alarm rates, with an eye towards evaluating the performance of his system on field data collections and demonstrations. His recent results are focused around the fact that both two-dimensional and three-dimensional convolutional neural networks have been designed for multiple data representations. And so by multiple data representations, we mean that Dave is looking at both the standard imagery that I have been showing here, but also spectral domain or wave number domain representations of the data that can allow us to extract information about the spectral clues and the frequency content and the direction of scattering that munitions and objects of interest might have. And the goal is to deliver ATR algorithms for the SVSS and the MUST to end users in live site remediations. So in conclusion, this program has really focused on building a purpose-built sensor for detailed ordnance surveys in very shallow water. Our prototype demonstrations have shown that we have the ability to accurately image and localize buried ordnance, the science targets, and clutter. And one of the things that we've really focused on is in trying to build up strong collaborations within SERDP's machine learning research community to help those teams leverage physics-based insights into the scattering mechanisms that we believe can help distinguish man-made objects from clutter to improve ordnance detectability. The benefits to the Department of Defense are that we want to provide a purpose-built sensor for detailed ordnance surveys in less than 5 meters of water. That's our focus and our goal, and really the focus is heavily towards the shallower end of that. How can we push to water depths as shallow as 1 meter? We're continuing to develop the algorithms and hardware to conduct near-field synthetic aperture sonar imaging. So as we learn more about the sensor, as we improve our hardware, we are adapting our algorithms and improving those. And then we're providing data sets within SERDP's machine learning community to advance the automatic detection, to advance the automatic detection of munitions. Okay. With that, I wanted to once again thank Dave Bradley and Rula and her team for the opportunity to speak here, and I'm happy to take any questions.
Wonderful. Thank you so much, Dan. We've received a tremendous list of questions. So we're going to start with one from the Lawrence Berkeley National Lab. Do you use a broad range of sonar frequency or a single sonar frequency? And if late time scattering is caused by a resonance effect, would it be of some interest to find out the resonance frequency and its relationship to the geometry of the target object?
That's a great question, and I'll do my best to answer both parts of it. So yes, we use a broad band of frequencies with the prototype projectors that I described that leveraged the existing elements. That design actually had some drawbacks associated with the fact that we were leveraging something that wasn't built for this purpose, and it limited the range of frequencies that we could operate with. So that device we operated from 20 to 35 kilohertz, and we really had a challenge in that the device was a highly resonant device, which meant that for the very short pulses we wanted to put into the water, we were exciting the device's natural resonance frequency, and it really made some of our imaging approaches challenging. Our new device that we have built has a very low mechanical quality factor. Hearing the word low quality sounds scary, but in this application, it's actually a very good factor. It allows us to create very high fidelity waveforms in the water. We can transmit very, very short bursts of energy, and we are now transmitting over a much wider range of frequencies from 12 to 44 kilohertz is our new operating new operating range. So we're using linearly frequency modulated pulses that are tapered, and then transmitting from 12 to 44 kilohertz. The question of is a really nice one. Is if we if I paraphrase it incorrectly, please correct me in the Q&A. If we could know the resonance frequency of the object, would we want to just transmit there? I think that's the gist of your question. I think the answer is yes, but I think that it is unknowable because frequently these objects that we might find in a realistic site have a wide variation in their composition and their structure. So as from what I have seen, I don't think that we're ever going to be able to get to the point to say, like, okay, we're looking for object A and it's resonant at this very specific frequency. Therefore, if I see resonance at that specific frequency, I'll know that it is this object. Instead, I think we're looking for something that's a bit broader in scope, and so we're looking for the presence of resonance and resonance around a range of frequencies. I appreciate the question.
Wonderful. All right. Well, this next question is from Bay West. Would focusing on the late time return and turn height or disturb the return from another man-made object that happened to lie directly underneath the topmost object?
Yeah, it's a good question, and it's something we've worried about in the sites that in the test sites that we've prepared. We have very few cases where we've intentionally placed objects closely enough that we were going to be scattering from two objects simultaneously or within the same volume. We do have cases where we have done this, but that's not a problem that we've been exploring. But certainly that'll be a challenge, right? If we end up in a configuration where we have one object, at a shallower depth than another, but they're at the same along track and cross track position, certainly the late return from one object could obscure the other. And then this choice of applying this fixed range focusing would then cause that later object to defocus. I think how to handle that robustly in a signal processing pipeline, at least in my mind, is still an open question from a signal processing research perspective. And it may be something where you just want to flag that is happening, and it might be something where a human needs to assess the data.
Great, thank you. This next question is from the Naval Research Lab. the frequencies that you have used are in the range of marine mammal sensitivity. Is that of concern?
Yeah, yes, of course. It's always a concern. Fortunately for us, the two sites that we have operated, at, the local freshwater lake that we have here in Howard, Pennsylvania, doesn't have marine mammal concerns, and then the experiment that we did at the Aberdeen Test Center was in a controlled facility that is flooded and drained by them, so no potential for exposure to marine mammals. But any live site demonstration that we might do where marine mammals might be present and might be impacted by these operations would obviously be done with a complete environmental assessment to ensure that we were operating in a way that complied with any rules and regulations regarding how to safely operate this type of sonar system and the source levels and ranges of frequencies that are used.
Thank you. And a follow-on question from the Naval Research Lab: have you investigated non-metallic objects such as plastic or wood?
Yeah, so we have it's actually interesting, and it's one of the examples that I nearly included in the brief. We for our science objects, we use a number of cylindrical objects, both solid aluminum cylinders and steel pipes. And as an example of trying to deploy a non-resonant object that would have the same geometric characteristics, we actually formed cast concrete cylinders. So we have solid concrete cylinders that are in our field. Additionally, for a standard clutter object, we have a number of cinder blocks in our field. So yes, we have scattered we have many looks at non-metallic objects in our field.
Thank you. This next question is from Woods Hole. For visualization, have you tried 3D ISO surfaces to create an output that can be viewed in 3D with rotation of the view?
Yeah, that's a really good question. And actually, if you look at the example that came out of the collaboration with Arizona State for the neural volumetric rendering, Albert Reed was the PhD student who did that work, and Albert was using ISO surfaces to try to visualize that. It's not something that I have done yet, but it is a thing that I know and we know we need to dig into and try and understand that. The tricky bit with that is in automating the process of defining the level to set for that ISO surface. I think that would be the hard part or the tricky part of doing that. But I do think once you've identified a region where you say, hey, I think this is an object, maybe that would be something where you've identified an object, you've sampled it and said, okay, show me the ISO surface of this object. That might be a more productive way to pursue that. That's a good question, though. I appreciate it.
Great. And this next one is from the Pacific Northwest National Lab. Have you deployed your sensor from an autonomous sailing vessel or ASV, and what benefits can be gained from doing so, especially with respect to the SAS reconstruction quality?
We have not. The only platform that we've deployed from is the test platform that we have here at ARL. It is definitely something, as we start to think about transition of this sensor into ESTCP and how other groups might use a sensor like this. How do we deploy it from craft that aren't so specialized? It's also, if you can remember back to almost an hour ago when I was showing the diagram that was the prototype layout and the purpose-built layout, you'll notice that the fore-aft dimension of the sonar hardware that's required under the new purpose-built layout is quite short, right? So we're talking about something that's maybe only 20 centimeters in the fore aft direction. It's about 1 meter, 1.2 meters wide. So it starts to look like a wing, and I do think in that geometry it becomes much easier to think about how we would deploy this from craft of opportunity. I have to say I haven't specifically thought about autonomous sailing craft. Instead, I've thought more about what I've seen as the standard deployment for multi-beam systems that are the kind of rigidly affixed pole deployed over the side of a boat, and whether we could get a wing onto something like that. But I think moving beyond the current test platform that we've used as a prototype platform to a broader range of platforms is definitely a set of engineering questions that we're going to have to address now that we've come through the design of the purpose-built hardware.
Great, thank you so much, Dan. Just a follow-on question to this one before we move on. If you were to use an ASV, what limitations would exist in doing so?
Oh, I think I think the only so I guess one, in not being extremely knowledgeable about ASVs themselves. So if you want to follow up with me offline to maybe help me understand if there's something that I'm not appreciating in the response I'm about to give. The only requirement that we have is we need the inertial navigator to be rigidly coupled to the receive array. So all the challenges that I think about in packaging this is how do we make sure that the inertial navigator and the receivers are rigidly mounted relative to each other, so that we know the position of the sonar system. Beyond that, I would think that the only questions would be around the idea of size, weight, and power, and whether the vehicle had enough propulsive force for the added drag associated with the sonar system itself. That being said, if you want to follow up offline, I'm more than happy to have a discussion.
Thank you so much, Dan. This next question is from the California Department of Toxic Substances Control. What is you said that the sensing works best in shallow environments. What's the maximum depth of sediment for sensing, and do different soil types lower the quality of the data?
Good. So, Rula, could you just repeat one last little bit? Do different what types?
Do different soil types
different soil types. Okay, yes,
yep, of the data.
Good. Excellent question. So what sets the maximum ability to image into the sediment, maximum imaging depth into the sediment, is going to be the soil type. So different soil types will have different compressional wave attenuation factors. So typically we describe that in some number of decibels loss per wavelength propagated, into the sediment. Sediments like sands, coarse sands, can have relatively high attenuations, whereas very soft river silts can have very, very low attenuations, and you can get a large amount of penetration into the bottom. For us, the site where we've seen the greatest penetration depth was an actual test of opportunity that we conducted off of the Aberdeen Proving Grounds in the Bush River, and in that site we were surveying and just collecting data against clutter objects of opportunity. We were able to resolve an object that was maybe 20 centimeters in length, 20 or 30 centimeters in length, by about 10 centimeters in width, at a burial depth in excess of 3 meters with 2 meters of water above it. So the maximum stated range for the SVSS is 5 meters range from the sonar, and so that was a case where we were imaging an object kind of right at the maximum design range for the system. But it was clear that if we had modified the mode of operation, we could have penetrated further. But I think that was really aided by the fact that the river sediments there are extremely soft and very easy to propagate sound through at the frequencies that we're operating at.
Okay, great. And a follow-on question from the California Department of Toxic Substances Control. Specifically, have you performed any testing in a marsh environment?
We have not.
Okay, great. This next question is from a retired fisheries scientist. Do reflective or metallic components in bottom sediments, things like iron rust, affect depth, range, or accuracy of your scanning method?
Good question. The only way that I can think that it would have an effect is in line with the answer that I just gave, and that is if the presence of those types of materials is correlated with an increase in compressional wave attenuation. So the fact that the material might be might have iron dust or some metallic nature should have no effect on the propagation of sound. So its metallic nature shouldn't impact it. But if it was correlated with something in the nature of the sound that would be associated with sediments that have high compressional wave attenuation, then it would impact it. But in and of itself, no, I don't think it would have an impact.
Great. And one last quick question before we wrap up. Do you have any development plans towards miniaturization of the sensor that might be appropriate for integration into small unscrewed vehicles? And this question is from the Johns Hopkins University Applied Research Lab.
Yeah, it's a great question, right? How can we make it smaller? The reality is, I touched on the fact that the way the sonar system operates is in the along track direction. We're doing synthetic aperture sonar image reconstruction methods. Those methods allow you to have a very small sensor and still be able, if you can transit the scene in a proper way, you can still achieve reasonable imaging ranges and still achieve maximum full image resolution. The real challenge is in that cross-track direction. And in that cross-track direction, the way the system is currently constituted, it is a real aperture sonar system. And in a real aperture sonar, we need the aperture to be large to provide us with a modest amount of ability to resolve things in that cross-track direction. The only way that I can see overcoming that and getting it to a form factor that would be small enough to deploy from let's say a modest size unmanned underwater vehicle would be to leverage something like making repeated passes in orthogonal directions and being able to potentially coherently process those. There's some real challenges in the navigation and signal processing to do that would need to be addressed first. But appreciate the question.
Great. Thank you, Dan, for a phenomenal job with the webinar and with addressing the questions. We're going to go ahead and wrap up. Our next webinar is on Thursday, December 7. It will focus on DoD-funded research efforts to develop forensic PFAS methods for source tracking and allocation. This webinar will feature two speakers, Mr. Jared Dregland from the National Institute of Standards and Technology, and Dr. Jens Blotvogel from Australia. Registration is open, so please visit the SERDP and ESTCP webinar webpage for registration information. And before we conclude, I'd like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it if you can please take a moment to complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you for joining us.